Okay, we're back for patterns of inheritance. This may be a longer video because we have a lot to cover. I like to call it fun with Punnett squares and pay attention to that because these little boxes here that you see can really help you predict the inheritance of at least single gene traits. Punnett squares, are great for that. As you get into polygenic traits, you need more boxes. It gets a little more complicated. We're not going to do any of those, but do pay attention to that. Some terms and conditions as they apply to patterns of inheritance. We have the term allele. That is a variation of a specific gene. For example, there is a gene that governs your blood type. There are three basic alleles, A, B, and O. You get one allele from your mom and one allele from your dad. That makes up a gene pair. A single gene trait or monogenic trait is a trait that's governed by the input from one gene pair. So on that one gene, you have all the material you need to express a given trait. More genes or more traits tend to be polygenic. Those are traits that are governed by the input of more than one gene pair. To give you a decent analogy, it's a difference between do, re, mi, single notes. You only need to press one key on that piano to make that sound. A polygenic trait is more like a chord. You need to press several notes and you need to play them in a sequence to make a more complicated song. So, single gene inheritance, more terms and conditions. We have the genotype, which is the exact composition that is present. It is both alleles from your mother and father working together for any given trait. Phenotype, on the other hand, is the trait that expresses itself, and it depends on the following other definitions. We have dominant traits. These traits always express themselves, whether their partner is dominant or recessive. If they are the same or if they are different, that dominant trait will always express himself. Recessive traits hang in the back. If somebody is dominant, they will not speak. But if they are among other recessive partners, they will express themselves. So they only express themselves when you are homozygous recessive for a given trait. You probably know these terms, but let's go through them anyway. Codominance occurs when both alleles are expressed, but they're different, so their traits are expressed at the same time. An example of this could be going back to that blood type analogy. The allele for type A is dominant, the allele for type B is dominant. When they are together, when you inherit one allele from your mother and it's A, and one from your father and it's B, they will both express their characteristics. They will both have the antigens specific to that allele. So they both express equal traits at the same time, but they are different. Related to that, we have incomplete dominance. Now, if codominance was two people talking at the same time, both saying different things, incomplete dominance is both traits expressing themselves, both people talking, but they're saying this like something together. They have made a compromise. They are blending the phenotype. It is not a blended genotype. When meiosis happens in the germ cells, the eggs and the sperm, you still have an equal chance of passing on either trait. You're not going to pass on the blended trait. But when they are expressing themselves, they sort of have this intermediate effect. They present a united front. So if one was red and one was white, they come together and they're pink. An example of this in the human genome is when a person has one allele for curly hair and one for straight hair, their phenotype will have wavy hair. They don't pass on wavy haired alleles. They pass on the straight ones and the curly ones, half and half. But their phenotype will show that wavy hair, not quite curly, not quite straight. Examples of common single gene traits are blood type, dimples, all the things you see on this list, color, vision. They're kind of easy to isolate. They make great examples for Punnett squares because you're only dealing with one allele on each, one pair of alleles. Single gene disorders that are really common. cystic fibrosis, sickle cell disease, PKU disease, one type of muscular dystrophy, Tay-Sachs. These are found on one gene. They are the most strongly associated genetic disorders because it's very easy to trace patterns of inheritance, even without a lot of genomic information. You know that they either skip generations or they're expressed very typically for single gene traits. They're also called autosomal disorders. Um, we have recessive and dominant, and just like you would imagine, a single gene recessive trait is only expressed when both copies of that gene are recessive. So you have to be homozygous recessive to have the disease. Your phenotype will only show that when you have both genes. Your genotype could be one of three things. You can have homozygous recessive, homozygous dominant, or heterozygous. If you have one copy, you'll be a carrier. You will have one allele for that recessive disorder and one that is normal. The normal one's expressing itself, and the recessive one might get passed on or might not. Dominant, if you have that trait, you will always have that disease. The trait will always express itself when it's present. Huntington disease was an example of that. It occurs later in life, but if you have that gene, it will express itself sooner or later. Let's see how that plays out in a Punnett square in real life. And kind of pay attention here because we're going to cover this concept. And when we have to predict a person's likelihood of passing on a single trait disorder, single gene trait disorder, these are helpful in explaining how that happens. So we have a mom, she's heterozygous for sickle cell anemia. She's got a big S, and that's normal hemoglobin, and she's got a small s, and that's the sickle celled shaped hemoglobin. So she has this, and she has this. Dad is homozygous dominant. He has all normal hemoglobin genes. So if we fill out our Punnett squares, and we do it correctly, take your time with it, you'll see that in the end, we have big S, big S, big S, big S, 50% normal genotype. 50% has big S, little s, and 50% are carriers. They have the sickle cell trait, but not the disease. Okay, let's do it again. But this time, mom has sickle cell anemia disease. She has both traits for sickle cell, and she has those characteristics, shaped cells that cause sickle cell crisis. Dad is a carrier. He is heterozygous. So let's do it again. Mom has little s. Whoops, let's make her red, sorry. Little s, little s. Dad has the normal gene. He is phenotypically normal, but his genotype is heterozygous. So he has trait and he is a carrier. So let's see how this ends up. Let's fill out our boxes. Big S's in that box, little s's in that box, and then little s's going across. Mom has a 100% chance of passing on this allele. Dad has a 50% chance. So with any given pregnancy, remember every time there's a conception, you roll the dice all over again as if you've never done it before. We have 50% chance of being a carrier. We have the dominant trait for normal hemoglobin, but we have the trait. So 50% are carriers and 50% are homozygous recessive, and we have disease. You're starting to see how we use that Punnett square to figure out probability. All right, let's do it one more time with sickle cell anemia. Mom this time is a carrier and dad's a carrier. Okay, so mom, big S, little s. Dad, big S, little s. Let's go fill out our boxes. Make my big S's really big. Make my little S's really little. And you see what we have. We have right here, let me kind of see if I can highlight it in yellow. Do I have a highlighter? No, that's all right. That's good. So here we have normal. That's one box. So that's a 25% chance. Here we are heterozygous. Those are carriers. Two boxes are affected. We have a 50% chance of being a carrier. And here in pink, we have homozygous recessive, and that's a 25% chance of having the disease. So let's go. 25% carrier, normal. Two normal copies of the gene. Normal hemoglobin all around. 50% are carriers. Sorry for my chicken scratch. I'm using my finger as a stylus. And we have 25%, the remaining 25% disease. We have sickle cell anemia. And that's how that could work. All right. Okay, now we're looking at the autosomal dominant disorder. We have a mom who has the gene for Huntington's disease. Whether she has symptoms yet or not, she is going to get them because that trait, if she lives long enough, will always express itself when it's turned on, when it's coded to do that. All right, so let's go back to our H's. She is heterozygous. She inherited one disease allele from one parent. She inherited a normal allele from the other parent. Dad, he is heterozygous. Recessive, he has both genes are normal. There's no family history of Huntington's disease. So let's fill out our boxes. Normal, 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 normal. All recessive. And we have a dominant gene for Huntington disease and a recessive normal gene. And same in this row. Okay, so you see what we have here. We have two boxes that are heterozygous and have the Huntington's disease trait. Because it is dominant, it will express itself. It has no choice. And here, in these boxes down here, we are homozygous, but recessive, which codes for the normal genes. So we have a 50% chance of Huntington's disease, which are really lousy odds when you know what Huntington's disease is and what it does to the human body. And that's what we want to, we need that information to be able to counsel our patients about risk. They say Huntington disease runs in my family, and you get a pedigree and you see a lot of people with it. That's a person who should get tested if that's what they want. We kind of parsed that out on Tuesday a little bit with my former student who's got a family history of Huntington, and he was deciding whether or not to get tested and what to do with the results if he did. But we're moving on now. We're going to talk about codominant patterns. So things are not always cut and dry, dominant, recessive. Sometimes we have codominance, and like I mentioned before, I'm just setting this up for the next Punnett square. You have an A blood type allele from mom. You have a B blood type allele from dad. You will have AB blood type. You will not have A or B. It will be AB. They will both express their traits at the same time. The blood type for A, the allele for blood type A will code to make an antigen against B and vice versa. That type O blood will react to. But anyway, so these people have both anti-A and anti-B antigens, or A and B antigens. Type O is recessive. Let's move on to the next slide, and we'll do our little thing. So let's say that mom is heterozygous. She inherited an A blood type allele from one parent and an O blood type allele from the other parent. The O blood type allele is not expressing itself it is recessive. So she is A blood type A blood. Dad has homozygous alleles for type B. He is type B blood. And what that looks like here, mom has A. Whoops, sorry, I wanted to make that red, so I'll just go over it. And she is O. Dad has B on both alleles. So let's go across. Fill out our boxes, and we'll see what we end up with. And on this example, you can see 50% chance of AB blood and a 50% chance of B blood, because the B blood will always express its trait, and the O blood is recessive. So just to recap that, we have 50% type AB and 50% type B. All right. If any of that doesn't make sense, please let me know, and we'll go over it and we'll do more examples. It's kind of good to know that, and you might see it again. So let's go on to our next thing. Traits with variable expression. So some traits are expressed in a patient's phenotype, but they vary in expression, and there's no way to predict how mild or severe that expression or how big or little that expression is going to be. And the example I'm going to use is an autosomal dominant disorder. Okay, it's called neurofibromatosis. And we kind of know to look for it when we see a newborn that has a lot of these cafe au lait spots, or sort of these tan spots on the skin. It can be mild, and it's restricted to just maybe some coloration on the iris or some small tumors that don't cause any problems. They're benign and they don't impinge on anything. Or the disease can be severe. And the presence of that allele does not govern the severity of the expression. So, on the severe end, we have a child who has behavioral and sensory deficits. They could be blind. Deafness, I think, in one of the types of neurofibromatosis, with autoacoustic nerve damage, learning disabilities, intellectual disabilities. You can have large tumors that grow in all kinds of tissue. And when they press on other structures, they can cause pain and tissue damage. There's one version of it that causes extreme pain. No parent wants to see a child suffer. So I did take care of a couple once in labor and delivery that had pre-implantation diagnosis because they got genetic counseling that basically, let's see. Okay, let me just pause this video for a second and get it back. Okay, sorry about that. Here we are again. I didn't want to start over because this is probably like the 6th time that I've tried recording this video. But let's do the example of neurofibromatosis with a Punnett square. Mom is homozygous recessive and does not have neurofibromatosis. Dad's heterozygous and has mild neurofibromatosis. Each conception has a 50% chance of a child who has that disease. But there's no way to predict whether or not that child will have mild or severe symptoms. Dad had done very well for himself. He had a master's degree and a full-time job. He's capable of fathering children, obviously. It did not impact him that severely. He was able to pass on his genes. But there was no guarantee that this child would have that prognosis. This child might end up with a lifetime of severe pain and disability. And so when they went to genetic counseling and they were told, your child has a 50% chance of having this gene, and it could be very severe, they opted for pre-implantation genetic diagnosis. And that was sort of the function of a Punnett square there. Okay. X-linked recessive disorders, we're going to talk about this, and then when we're done with sex-influenced disorders, that'll be the end of this video. So in an X-linked recessive disorder, the gene is only on the X chromosome. Usually, if they are recessive, it will only be expressed if the only X chromosome has the recessive gene, has the affected allele, but because males don't get a second X chromosome, the prevalence is much higher in males. So females inherit two of these. If it's recessive, it's very likely that they're going to inherit one allele from mom and one allele from dad. The chances that they're going to have this X-linked recessive disorder is small. Males only inherit X chromosomes from their mothers, so they have a higher chance of inheriting the disorder if their mother carries that gene. Okay, let's see what that really means. Let's look at a Punnett square. So, mom is heterozygous for the X-linked trait for color blindness. She has color vision. She is phenotypically normal because that dominant trait that gives her color vision will always express itself. Dad has only one X chromosome. It's normal too, and he has normal color vision. He doesn't carry the trait. So let's see. I kind of already filled this one in, so you don't have to look at my, silly handwriting with the stylus. Mom has big X, little x. Dad has big X, Y. So fill out the squares. You go down and across. Our chances are big X, homozygous, dominant, unaffected. Let's get our highlighter out. Okay. Unaffected. Big X, Y. Unaffected. Normal color vision, right? Now, mom gives her daughter the little x, big X. She is a carrier. She carries the trait for color blindness, but because the dominant trait with color vision is expressing itself in her phenotype, she does not have color blindness. She can pass it on to her children. Now, when dad contributes a Y chromosome and mom has the color blindness gene, we have color blindness. And so it's worked out for you over here. 50% normal genotype. 25% has a normal phenotype, but is a carrier. They are heterozygous. So there's a 75% chance that your child will have normal color vision with every conception. There is a 25% chance that you will have a male with color blindness because you have the recessive gene with the trait for color blindness, and you have a Y chromosome that doesn't have the trait for color vision at all. So the only choice you have left is color blindness. And that's how that works with sex-linked disorders. But that's not the only way that are assigned sex, which is different from gender, by the way. Sex-influenced disorders can work. They're not all linked to X or Y chromosomes. Sometimes we have a gene for a trait and it's housed on another chromosome. It's housed on 11 or 15 or 22. It's activated by estrogen or testosterone. Example, male pattern baldness. It is a single gene trait. It is not on the X or the Y chromosome. It is housed somewhere else in the genome. The reason that women with the allele do not express the trait and men do is that testosterone activates the gene for male pattern baldness. So there's that interplay between the environment and the gene, and that's where epigenetics kind of comes in. Okay, now let me see if this is sort of our last slide on this, and it is. So take a break. We'll come back and do some more.